Hello, I'm Robert Miller, and I want to talk with you today about an assumption in multiple regression analysis called the linearity assumption. And I'm going to do that. I've already drawn here the y-axis and the x-axis of a graph here that I'm going to display for you to illustrate the linearity assumption and what we're looking for with the linearity assumption. So here's the y-axis, like I said, and here the y variable in multiple regression is our outcome variable. So we have some outcome variable, whatever it may be, outcome variable. And we're going to treat this in terms of a simple linear regression. So for giving this example about the linearity assumption, so we'll just be looking at one predictor on the x-axis. So here's our x-axis, and we have a particular predictor variable on it. Let's give ourselves a little bit more room here. So predictor variable and the x-axis. Okay. So with multiple regression, what we're looking at here for our multiple regression analysis is to test relationships that we're assuming exist between the outcome variable and each of our predictor variables in our model. And what we are assuming here is that if those relationships exist, that they are linear in nature. So what do we mean then when we talk about a linear relationship? So a linear relationship looks basically like this. And so I'll do it in terms of each of these dots representing an observation. And this is just an example of one of many relationships that you could have between the outcome variable and a particular predictor variable. We'll put some more observed values. These are all observed values, each of these dots. And we like to draw a line through those observed values as a way of describing the relationship between the outcome variable and a particular predictor variable. And so the line might look like this, okay? And that would be an example of a linear relationship. So generally speaking, not perfectly, okay, but generally speaking, as values go up on the predictor variable, values also go up on the outcome variable. And that's an example of a linear relationship. Now, if anyone is wondering what one of these dots is, I mentioned to you, we'll just highlight this one right here. I mentioned to you that each of those dots represent observed values, and each of those dots actually do represent observed values, because for any one of those dots, we have an observed value on x and an observed value on y. So it represents a combination of observed values for an observed value on the predictor variable and an observed value on the outcome variable. And so here is the observed value on the predictor variable, whatever that value may be. If we're at 0 here, perhaps that observed value is 5. And so that'd be a 5. And then we have that dot also representing an observed value on the outcome variable. And perhaps that observed value in the outcome variable is, let's say 15. Okay, so here it'd be 5. Well, here it'd be 15. So it'd be a 5, 15 observed value combination, so to speak. Observed value of 5 on the predictor variable, observed value of 15 on the outcome variable. And that's then the case for each one of these dots. They represent a combination of observed values, one of those observed values being on the predictor variable and the other observed value being on the outcome variable. Okay, and so if we were to track these combinations of x, y observed values in this linear relationship, best described by this linear function through all of these observed values of x and y variables, we would find that generally speaking, as values increase on the predictor variable, they also increase on the outcome variable in this particular function for this example here. Okay, so that's what we're assuming when we're doing multiple regression and we want to test. What we're assuming will be linear relationships between the outcome variable and each of our predictor variables. In a model that involves more than one predictor variable, this would be with each of the predictor variables, that those relationships are linear, which means as values increase on the predictor variable, generally speaking, they also increase on the outcome variable. And that is as distinct from a curvilinear relationship. So if I can find my eraser here, that would look something like this. And there's lots of examples of curvilinear relationships, so this is just one. There's also lots of examples of linear relationships. This is just one example here as well. But here's an example of a curvilinear relationship, and this would violate the assumption of linearity for a multiple regression analysis. If instead we saw something like this, okay, so these are observed values here. I don't know if people can hear the sirens outside. Not very much of a siren sound, but these are the sounds of teaching in an urban environment. So anyway, I don't know if you're hearing that outside or not. Okay, so now you'll notice what happens here. The line that best describes the relationship between the outcome variable and this particular predictor variable now would be called curvilinear, and more specifically, this would be called a quadratic relationship. So for a while, as values on the predictor variable increase, so do values on the outcome variable. But then at some point that starts to level off, and so you get continuing increases on the predictor variable, but the values on the outcome variable level off with increasing values on the predictor variable. That's an example of a curvilinear relationship, specifically called a quadratic function or relationship between the outcome variable and this particular predictor variable. And that would not be a linear relationship, so that would violate the linearity assumption. Okay, so these linear relationships that we're assuming can take different forms. But what they all hold in common is that they're linear relationships between the outcome variable and any particular predictor variable. So you perhaps might have, again, these are observed values. Each one of these dots representing an observed value on the x variable, the predictor variable, and on the y variable, the outcome variable. XY combination for each one of these observed, each one of these dots represent this combination of observed values. And here you notice we draw a line through that. And now that's a linear relationship. That's a linear relationship. It's in a different direction than the one we saw before. So now, generally speaking, as values increase on the predictor variable, values are going down on the outcome variable. Okay, they're going down on the outcome variable. Okay, so now values on the predictor variable increasing, As they increase, values on the outcome variable go down. So the values on the predictor and outcome variables are moving in opposite directions from one another. And that'd be called a negative relationship. But anyway, it's a linear relationship as well. So the linear relationships can occur in different directions, but in both cases, they're linear relationships. And returning to the example I showed you originally, it looked like this. And by the way, this is a pretty strong linear relationship because the dots don't vary from each other all that much. You draw a straight line through that. And you do have some, probably want to do this better, go out like this a bit. It's more in the middle now of all the observed values. You know, there's certainly some dispersion from the line, but it's not, all that wide. So this is a pretty strong linear relationship. And this is what we saw before. Values on the predictor variable increase, so do values on the outcome variable. But of course, this can look a variety of ways for having a linear relationship. This is one example of a linear relationship, but it can look other ways. And so you may have been reading about, the slope of the relationship between the outcome variable and the predictor variable. And here we would have a strong linear relationship. I can draw my straight lines better. But a strong linear relationship between the outcome variable and the predictor variable. Because we can see as values on the predictor variable increase, the values on the outcome variable are really increasing at a fast pace. That's a strong linear relationship. But a linear relationship. So you'll notice that the one thing that all of these examples I'm giving you have in common is that we have a linear relationship present. The only exception to that was that curvilinear relationship I showed you, that quadratic relationship. But if you have this pattern of observed values, well, again, a linear relationship, but not quite as steep of a slope as we had here. And so the strength of the relationship is not quite as strong. So as values go up in the predictor variable, they go up in the outcome variable, but not quite as rapidly. And then you might have something like this. That's, pretty flat. And so that's, again, a linear relationship. As values are going up in the predictor variable, they're also going up in the outcome variable, but they're going up on the outcome variable pretty slowly with increases in values on the predictor variable. So, this is a weak linear relationship, and it might not even be significant if you were to test it. But in any event, regardless of the slope of the linear relationship, here it's pretty shallow, here it's steeper, and here it's a steep slope, which tells you something about the strength of the linear relationship between the outcome variable and the predictor variable. In each case here, you have a linear relationship. And that is the assumption then in multiple regression. We talk about the assumption of linearity. We want to see these straight line functions describing best the relationship between the outcome variable and each of the predictor variables, as opposed to what I showed you earlier, having some sort of curvilinear relationship, like a quadratic relationship, and other types of curvilinear relationships. You can read about those. But anyway, they are not straight line functions that best describe the relationship between the outcome variable and the predictor variable. Assumption in multiple regression is that the relationship between the outcome variable and each of your predictor variables, if you're testing hypotheses having to do with linear relationships, which you expect to be linear relationships, is that you will have a straight line function best describing the relationship between the outcome variable and each of your predictor variables. And you can test for that. And if you see that's not true, then in some cases you have a curvilinear relationship between the outcome variable and the predictor variable, well, then you're going to need to change your model, because a multiple regression model that only assumes these linear relationships, but that's not actually true when you test for it, that's going to lead to a regression model that is not stable and does not give you good estimates of your regression coefficients. So that's the linearity assumption in a nutshell, and thank you very much.